Hello, grade 11s. In today's lesson, we're going to be looking at stoichiometric calculations. And without any further ado, let's just get right down to the lesson. So we have this question 6. It says, in an experiment, a learner added 1.5 gram of sodium carbonate. Then we are given the chemical formula. So hydrochloric acid, a volume of 306 centimeter cube. So we can see that we are given the volume here, but this volume is not in the desired SI unit. So what must we do? We must say 306, divide that by 1000, and then we're going to have 0.306 dm cube. So this is now in the desired SI unit. And then we are told that this volume is of carbon dioxide, and then it was formed and collected under standard pressure at room temperature. Then take the molar gas volume at room temperature, Vm, as 24.45 dm cube. Right, so normally we have our Vm as a constant of 22.4 dm cube. But if the statement says 24.45, or if the statement gives you a certain molar gas volume to use, then you have to use the given molar gas volume and not this one. Okay, so now, which is why I always stress that you need to read your statement and highlight every bit of information that you are given there. Then, okay, take the molar gas volume at room temperature as 24.45 dm cube. We know that STP relates to anything that is a gas, right? And looking at this unbalanced equation, we can see that the only thing that is a gas here is carbon dioxide, as we are told that the carbon dioxide was collected at standard pressure and also room temperature. Right, so that's STP, standard temperature and pressure. So the CO2 here, the data that we have, the volume and the molar gas volume relates to what? To carbon dioxide. Right, now 6.1.1 says define the term 1 mole of a substance. Let's deal quickly with that one. So it says 1 mole of a substance is the amount of substance having the same number of particles as there are atoms in 12 grams of carbon-12. So this is how you are expected to define it for 2 marks according to your CAPS document. Then 6.1.2 says balance the equation for the reaction. Now, when it comes to balancing, it's just a matter of looking at these elements and counting the number of moles of each element in the right hand side and the left hand side, the reactant side and the product side. So now starting with sodium here, we can see that sodium, we have 2 atoms of sodium, but here we only have 1 atom of sodium. So how can we balance the number of moles here? We can just put 2 in front of sodium, which will make us to have 2 sodium atoms. Now let's come to carbon. Carbon, how many atoms do we have on the left hand side? Only 1. And then here also we have 1. So do not be confused by this C here. This is chlorine, right? This is Cl. Then this is carbon alone. And this is another carbon alone, so 1, 1. And then oxygen atoms, we have 3. And then this side, we have a total of 1 plus 2, it's also 3. Then what else is not balanced? It's the hydrogen atoms. So we have 1 here, but this side we have 2. So how do we balance? Easy, we just put 2 in front of HCl. And then if you can just check chlorine, now we have 2 atoms of chlorine, and then we also have 2 atoms of chlorine, right? So that's how you have your balanced equation. Let's write it in full. So we have Na2CO3 plus 2HCl, and then yield 2NaCl plus H2O plus CO2. That's your balanced equation, right? Okay, so we have 6.1.3. It says calculate the mass of sodium carbonate that reacted. Now you will remember what I told you. I said when it comes to stoichiometry, the trend that you'll be given here, or the type of questions that you'll be given, is whereby now they will give you information on one of the compounds here, but then they will ask you to find the information or the value on a certain compound of which you are not given information on. So you can see that we are not given anything on sodium hydroxide or on sodium carbonate, except that a learner just added 1.5 gram of sodium carbonate. So that's the only thing that we are told there. But then it doesn't suffice much for us to calculate the number of moles, the mass that reacted here, the mass of sodium carbonate that reacted. So how do we do that? So we can see that we were given the VM here. So the first thing that you want to have is your data box, right? So data, so we have VM, it's 24.45 dm cube, and then we have the volume which we already we already converted to dm cube, so it's 0.306 dm cube. And then remember, all this relates to carbon dioxide. So now having to say that we are given all the information on carbon dioxide, we can now calculate the number of moles of carbon dioxide, and then we have to use our ratios in terms of the coefficients, and then from there on we can calculate the mass that reacted. So I will just have to write that in steps so that you understand, and you can pause the video and follow through with the steps. So step number one, we just calculate the number of moles of CO2. So we are aware that we do not want anything, we do not want the mass of carbon dioxide. But then since we are given the information on carbon dioxide, the first thing that we have to do is to calculate the number of moles. Remember, all the four formulas that we have on stoichiometry, they all have a common factor of the number of moles. All formulas have this n, the number of moles. So you can understand from that the primary thing to do in stoichiometry is to calculate the number of moles. So if you ever find a question you don't know what to do, the best thing to do is just to find the information that will enable you to calculate the number of moles. Then V, we have 0.306 over 24.45. Then at this point you just punch all that in your calculator, so you'll have 0.0125 mole, right? So now we are aware that this is the number of moles of carbon dioxide, right? But then what are we looking for? We are looking for the information on sodium carbonate. So now, having to use our balanced equation, we can see that the ratio of sodium hydroxide to the carbon dioxide here is 1:2. The ratio of sodium carbonate, sorry for that, the ratio of sodium carbonate to carbon dioxide is 1:1, right? So what does that mean? It means that, so the ratio of sodium carbonate to carbon dioxide is 1:1. This means that the number of moles of carbon dioxide is the same as the number of moles in the sodium carbonate. So if we have 0.0125 mole here, that means we also have 0.0125 mole, because they share the same ratio. So in other words, same ratio, same number of moles, right? And then, okay, so now that we have the number of moles, of sodium carbonate, that means now we can use this number of moles to calculate the mass, right? The mass that reacted. So this would be our step number 2. Let's refer this as to our step number 2. So step number 2 would be to use the ratio coefficients, right? So we use ratio coefficients. And then step 3 would obviously be to calculate for the required value. So now we'll go back to the question and actually find what are we looking for here. We are told to calculate the mass, right? So that's what we're gonna do now. So we have N is equals to M over big M. Remember, now we are using the number of moles of sodium carbonate, 0.0125, and then M, that's what we are looking for. But then the molar mass, it's the molar mass of the sodium carbonate. And now we have this. So the molar mass, remember, we are using the molar mass of the sodium carbonate. So we just look this up in the periodic table. We have Na. Na gives us 23, but then we have 2 atoms of sodium. So it's 23 times 2 plus 12 plus 3 times 16. That will give us 106. Then you cross multiply here. Your mass will be 1.33. Okay, let me erase here. So we have 1.33 gram, rounded off to 2 decimal places because that's your final solution. Okay, so now we have 6.1.4. It says calculate the percentage of sodium carbonate in excess, right? So to calculate the one in excess, you will realize that the one that we calculated in 6.1.3, the mass we found it to be 1.33 gram. Which tells you that from the 1.5, not all of this 1.5 reacted. So we can say the sodium carbonate was in excess, right? So Elena added 1.5, but only 1.33 reacted. Now we must calculate the percentage of sodium carbonate in excess. That means the sodium carbonate that did not react. So that one should be pretty easy. We can just start by calculating the mass of unreacted. So this is the mass of the unreacted sodium carbonate. Then we will say 1.5 minus 1.33, which should give us 0.17 gram, right? But then remember, we want this as a percentage. So as a percentage, how are we going to express that? So we'll say percentage of excess or the percentage of the unreacted. Remember, excess and unreacted means the same thing. If it did not react, that means it is in excess. So we can say 0.17 over the total mass that was added to the reaction mixture. Then 0.17 over 1.5. Multiply that by 100 because we are trying to find it as a percentage. And then if you punch all that in your calculator, you'll have 11.33%. That's how you have 2 marks. Awesome. Okay, so we have 6.2. It says, learners prepare a solution of sodium hydroxide in water by placing 8 gram of sodium hydroxide in volumetric flask and adding water to produce 250 centimeter cube of solution after stirring. Then 6.2.1 says define concentration in weights. Let's run quickly to that. So we say concentration is the amount of solute per unit volume of substance. That's how you are expected to define it for 2 marks according to your CAPS document. Then 6.2.2 says calculate the concentration of the sodium hydroxide solution, right? So in order to calculate the concentration, let's look at the information that we are given. We are given 8 gram here, and then we are also given the volume 250 centimeter cube. Now we can see that this volume is not in the desired SI unit. We need our volume in decimeter cube. So what must we do? Say 250 divided by 1000, and then we'll have 0.25 dm cube, right? So that is our volume in the desired SI unit. So our data box here will include the mass, which is 8 gram, and then we have the volume, which is 0.25 dm cube. Now let's check to what does this relate to. It relates to the sodium hydroxide, right? So we are told that 8 gram of sodium hydroxide in a volumetric flask in adding water to produce 250 centimeter cube. Then we are required to calculate the concentration, of course, of the sodium hydroxide. Then, of course, for this one, we know that when it comes to calculating the concentration, we have 2 different formulas. It's C is equals to N over V, or we have this one. So in your formula sheet, you find that it is written like this, right? So we know that this one we use it when we have the number of moles, and this one we use it when we have the mass. From this one we can see that we already have the mass, so we know the choice of formula is this one. That means we have to look for the molar mass. So how do we find the molar mass? It is simple. We look at our periodic table. What is Na 23, and then oxygen 16, and then 1. and then adding that together will give us 40 grams per mole. Then what are we looking for? We are looking for concentration, so put a question mark there. Then you can see that all this data that we have here corresponds to this formula here. That's how you choose the correct formula. So to answer 6.2.2, we just say C is equals to M over M times V. Then what is your mass? The mass we were given as 8 gram, and then the molar mass we calculated it to be 40. Then the volume convected is 0.25. Then it's just a matter of punching all this in your calculator. So you have 0.8 mole per dm cube, right? Remember that is the SI unit for concentration. Okay, so now let's look at 6.3. It says sodium azide, which we are given the chemical formula here, is used in car airbags. For the airbag to inflate, the following reaction must take place. So the sodium azide must decompose to your sodium and your nitrogen gas, or break down to sodium and nitrogen gas. Then here we have calculate the volume of nitrogen gas that will be produced at STP if 55 gram of sodium azide reacts completely. Now we know once they touch upon the word STP, we know that relates directly to anything that is a gas here. So we can see that they say the volume of nitrogen gas that will be produced of what? Nitrogen gas, right? But then since here we are not told of any STP, of any molar volume value to take, that means our molar volume will remain a constant of 22.4 dm cube, because you can see there is no statement that says take molar gas volume as a particular value. So that means if that statement is not there, you just simply take it as 22.4. Right. So now, again, remember with stoichiometry, we wanted the volume of nitrogen gas, but we are not given anything on nitrogen gas except that we are told that it is produced at STP. This 55 gram here, they say if 55 gram of sodium azide reacts completely. So this 55 gram here speaks to the sodium azide. So once again, you can see the trend the trend happening again here, whereby we are given the information on this compound here, but then we are looking for the information on this compound. So now what must we do? We must calculate the number of moles of this given compound, use the coefficient ratio, and then now we can calculate for the required value. So again, let's put it in steps. So hope you still remember step 1. We said is to calculate. So in this case, we'll calculate the number of moles. So number of moles of what? Of sodium azide, right? So it's NaN3. Then to calculate that one, we already have the mass. So the formula to use is this one, of course. Then 55. Our molar mass for sodium azide, this is 23 plus 14 times 3. This will give us a 65. And then if we punch all this in a calculator, we will have 0.846. So allow me to round off to 3 decimal places because this is not the final answer. Then step 2 is to use ratio coefficients. So use ratio coefficients. Then that means we will have to go back to this balanced equation here. We can see that the coefficient of sodium azide is 2, and the coefficient of the one we are looking for here, which is nitrogen gas, is 3. So now comparing this in terms of the ratio, we'll say the ratio of sodium azide to that of nitrogen gas is what? Is 2:3. According to our coefficients in the balanced equation, as we can see there, right? So this is 2:3. What does that mean? This means here we have 0.846, and then obviously here the ratios are not the same, so we'll have to calculate for the number of moles of this one. So it's just a matter of cross multiplying here. We will have 2x, and then if you take 0.846 multiply it by 3, you will have 2.538. Then obviously to look for x, you'll have to divide both sides by 2, and then the number of moles of nitrogen gas will now be 1.269 mole, right? So that is the number of moles of nitrogen gas. Now that we have the number of moles of nitrogen gas, let's move to step number 3, which is now we will have to calculate for the required value. Calculate for the required value. So, okay, now remember they touched upon STP, and then we know the only formula that will that is allowed to be used when they say STP is this one, N is equals to V over Vm. So we already have the number of moles, we are looking for the volume, and then the Vm is a constant. So we have 1.269 is equals to V, then the Vm will be 22.4 as given in our data sheet. And then here we cross multiply. This will give us 28.43 dm cube. And that's how you have your volume. So make sure that you follow these 3 steps correctly. And then obviously when it comes to stoichiometric questions, you will always get your answer when you follow these 3 steps carefully and diligently. Okay, so now let's look at question 8. It says 4.14 gram of solid lithium nitrate is first dissolved in a small amount of water and then made up to a certain final volume so that the concentration of the solution is 0.05 mole per dm cube. Then 8.1 says write down the definition of concentration again. So it says concentration is the amount of solid per unit volume of substance. So make sure you don't forget it. You can see that it has now appeared twice. Then 8.2 says calculate the number of moles of lithium nitrate used, and then that is only for 2 marks. So reading here, we can see that we are given the mass of the lithium nitrate, and then which to calculate the number of moles when given the mass, we know the formula goes as N is equals to mass over the molar mass, right? So the mass is 4.14, and then to calculate the molar mass, we just check the periodic table, and then if we add all that, it will give us 69. So 4.14 over 69, rounded off to 2 decimal places, we will have 0.06 mole, right? So that is 2 marks, so they will just mark like that. And then okay, 8.3 says calculate the final volume of the solution, and that is for 3 marks, right? So to calculate the volume, we can say that when we read further here, it is we are told that a certain volume is made up to a certain volume so that the concentration of the solution is 0.05 mole per dm cube. So you can see that already we have the number of moles from 8.2, and then we are given the concentration, which would enable us to calculate the volume. So the formula for that one is obviously C is equals to N over V, since we can see that we are given the concentration there. So our concentration is 0.05, and then the number of moles we just calculated to be 0.06. Then here we have volume. So to calculate the volume, we just have to swap the positions of this, then 0.06 over 0.05, right? Then if you punch that in your calculator, you'll have 1.2 dm cube, right? That's your 3 marks like that. So choice of formula, substitution, and correct answer. Then 8.3 says 8.4 says an additional 250 centimeter cube. So note what they're saying, an additional. So that means to the volume that we already have, they added another 250 centimeter cube of water to that solution. Then calculate the new concentration of the solution. Now let's speak about the volume. That means the final volume that we'll have here, it is not 250 centimeter cube, but now it is this 250 centimeter cube plus the volume that we calculated, right? So, but then remember one thing, this volume is not in the desired SI unit. So what must we do? It's 250 divided by 1000, then we'll have 0.25 dm cube, right? So what formula should we use for this one? Now, the formula, there is a specific formula for this one if you're looking for the new volume or the new concentration. So it's C1 V1 is equals to C2 V2. So this is the formula that we use if we are looking for either the new volume or the new the new concentration of a particular substance, either an acid or a base, right? So okay, now let's see. We have C1, which is, from this one we can tell that C1, this is for the initial, and then C2 and V2, this is for the final, right? So initially we had a concentration of 0.05 as given, and the volume that we had there before the water was added, of course, was 1.2, right? Then after the water was added, this is the concentration that we are looking for. But after the water was added, remember the water added to the volume that we initially had. So now that means V2 will be 1.2 plus the 0.25, right? Then adding this together, that means V2 will now be 1.45 dm cube, right? So we have 1.45 here. Then to calculate C2, we obviously have to divide both sides by 1.45, and then even here divide by 1.45, right? Then calculating C2, we will have, if you punch that in your calculator, you'll have 0.04 mole per dm cube, right? That's how you have your concentration.